Thank you. I don't know if the sound is okay. It's working? It's just for recording. Okay. Okay, I thought it was amplifying. Okay. Okay, so thank you a lot, Kevin, Idris, and Elisa for the invitation. Really nice to have a workshop on shape optimization from time to time. So, yes, I'm going to talk about the optimization of minimization diagrams. So the idea is, usually we consider this model shape optimization problems. So as we have seen many times already today, and usually you here solve the PDE or not. Now, of course, usually we are more interested in the PDE case. Here, most of what I'm going to show, there will be no PDE, but everything works also with PDE, and I'm going to talk a bit about the PDE case at the end. So as we know, there's a well-developed theory when omega is smooth, not to say that this is completely over, but there's already a lot of theory that has been developed, but still many interesting problems in the smooth case, of course. But here, I'm interested in studying problems with non-smooth shapes and several phases. So I just put two pictures here to show you what I mean, more or less. So a smooth case would be like you have one omega with a smooth shape, and you have two phases. You know? So this is the typical case, like with this level set method that we have seen in the previous talk. And here I'm interested in this kind of situation where you have a multi-phase and non-smooth shapes. So the non-smoothness, so here you have a set of shapes, now the omega case that create a partition of the domain. And the non-smoothness is very natural in this setting because of the intersection of the interfaces. You know? So you have this. So this is a simple case of Voronoi diagram. So, but you can see you have these triple points, which are interesting geometric objects here. And so a typical example is the Voronoi diagram, which is really ubiquitous in many applications, especially in numerical modeling. And we have seen in the previous talk, it was not really exactly a Voronoi diagram, but this K clustering, but this is the same, just here, it's in the continuous settings. And in the previous talk, it was in more like in a discrete setting, but the idea is the same. So you have some sites here, which are these red dots. And then the Voronoi region are the regions where you are closer to one of these sites. You know? So you can see that this interface, they are the points that are equidistant to two sites. And the triple points here, they are equidistant to three sites. You know? And the definition is just using the Euclidean distance, which is, so the set of points, the omega I is the set of points where the x are smaller, are closer to the AI. So this is here a simple example with 16 cells. And so the Voronoi diagrams, there are a particular case of something called minimization diagrams. So the idea is as follows. You have a set of indices, which I call this capital K, and you have a function phi, which is just a vector valued function. And then the cells, they are defined by the lower envelope of these functions. So you can see here I draw, I mean, this picture is not from me, actually, I took it from paper. So you can see this is the first function. This is the second function, the third function, and the fourth function. And the lower envelope is just the graph, which is the lowest part of all these functions. And you can see that the first cell is the region where phi1 is the smallest. The second cell is the region where phi2 is the smallest, and so on. You can see that these cells, they don't have to be connected. For instance, the first cell has a component here, and it has another component here because phi1 is smaller here, okay? So, and then the minimization diagram is just the union of all these cells. Or you can see the cells also as the region where the phi k is equal to the lower envelope. So, of course, in 1D, it's not really interesting, but it's good to show the picture to give an idea of how this works. And then starting from the second dimension, it starts to get interesting. You can see that you have these different phases. So here, this is the omega 0 is the region where phi 0 is the smallest. Omega 1 is the region where phi 1 is the smallest, and so on. And you can see that then you got some interface which can be curved, and you have these triple points, which are the region, like in the Voronoi cells, which are at the same distance from the different sites. So it generates some interesting geometries. And you can do this in any dimension, of course. And in 3D, it starts to get really interesting because you get all types of lower dimensional interfaces. And so you have, of course, the interior of each, here this is like a bubble, sub-bubble, which is 3D. You have the surface, which is 2D. You have the contact line, which is 1D, and you have this quadruple point, which is dimension 0. So if you are in dimension n, then you get all the lower dimensional interfaces from n to 0. So I think it's really nice because you can model some complex geometries with non-smooth shapes just with a single function phi. And so in the literature, this minimization diagram, they are studied mostly from the point of view of how can we build them? It's already a difficult problem. So already for the Voronoi diagrams, it's not so easy in 3D. In 2D, it's okay. But then you have all sorts of minimization diagram with some specific function phi. And then there's many problems on how can we build them numerically, for instance, or what are their properties. So here I'm interested in the problem of controlling them. So this would be two interesting situations. One is where the function phi is time dependent. And this I'm not going to talk about. I'm just going to talk about the case where phi is parameterized by a set of sites A. And the A, it's a vector of parameters AK, which are vectors of dimension Q. Okay? So they will play the role of control parameters for the shape of the cell. So here, think about the case of the Voronoi cells. Now you have the sites, and you want to move the sites around so that you can control the shapes of your cells. So you have a function phi, which is a vector-valued function, and it's in RD, but it also depends on this parameter, so it's also in RQ here. This is just a point. This is just a vector of parameters. It could be, or it could not be. For Voronoi, it happens to be just a point in space. But it also could be like some parameters which represent some distance. I'm going to show some examples afterwards. For instance, for the Voronoi case, the Q is equal to 2. I mean, it's equal to D in dimension D. So here are two examples. I've already shown the case of the Voronoi diagrams. And so in this case, the Q is equal to 2. And the AI then is this parameter here that appears in the definition of omega I. So of course, it's a particular case of minimization diagram with the phi k defined like this. Okay? And then another example of diagram is the power diagram, which is also used quite a lot in application, for instance, in optimal transports. So here it's like a more general Voronoi diagram. So you have this extra term here, this Ri square. So, and then the AI is the Ci, which is the position here, plus the Ri. So I'm not sure if the Ri would have a geometrical meanings, but the Ci is like in the Voronoi diagrams, okay? And this is also a particular case of minimization diagram with this type of functions. And then in the literature, there exist a lot of different diagrams, like Möbius diagrams, which are less studied, but there's a whole zoology of diagrams that are studied in the literature. But these two are some of the most used in applications. So the goal is to study the sensitivity analysis of this minimization diagram, mainly for optimization purposes. And then what we have done in this paper here is we developed a perturbation theory for sets which are defined as the intersection of sub-zero level sets of functions. So it's more general in a way than the minimization diagrams, which is a particular case of this perturbation theory. But I'm going to show examples. It will get clearer how we do this. So, and we can use this theory to compute the sensitivity analysis of these minimization diagrams, and also to study time-dependent minimization diagrams. The interesting thing is that this theory encompasses both the level set method and the optimization of Voronoi diagram, which, when I saw this, was a bit surprising to me because these two things seems completely different, level set method and optimization diagram. But in fact, there are two particular cases of these minimization diagrams. So this is an example where we consider these intersections of sets. So we have three circles. This is the full line. And the cell here that we study is this V of K. It's this Reuleaux triangle. It's like a triangle with curved edges. And these dashed lines, they represent the small perturbation of the circle. And so you can see when these three disks grow, then the Reuleaux triangle also grows a little bit. So we want to, so here the function that we define our problems are defined like this. So these circles, they are the sub-zero level set of this function phi k. So it's a very simple function here. And you can see the dependence here on the radius. So we make a small perturbation on the radius, okay? And now I'm going to explain how we can relate this to the usual shape derivative that we use a lot in shape optimization. So I don't think I need to explain a lot the concept of shape derivative because many of you are familiar with this. But what I want to emphasize here, so in a smooth context, we would define it like this. For instance, we have a perturbation of omega using a diffeomorphism, and we define a shape derivative by taking the derivative respect to t. But I'm also interested in the case where the shapes are not smooth. So for instance, typically polygons, or it could be curvilinear polygons, which are the cases of interest. For instance, if you look at the Voronoi case, then you have perturbation of polygons, basically. No? Even convex polygon, but it makes no difference. So let me explain you how this works in the context of this minimization diagram. So what we are used to in shape optimization is we do a compute derivative basically like this during a change of variables using the fact that omega of t is the image of some application, capital T, which is parameterized by a small time t. And then we have this formula for the change of variable. And then very often when we do optimization with the free-form shapes, theta is defined first, and then the capital T is defined using theta. And then we use a perturbation of identity or the velocity method to compute the capital T, and then we can parameterize the omega. We don't really care about what the T is because we are just interested in small perturbation of the shape for the optimization. But there are some cases where the shapes are given first via a parameterization. So in this case, the omega T is prescribed, is already a given. No? So in this case, if we want to compute the sensitivity, somehow we need to describe this capital T that corresponds to the omega T so that we can compute the derivative. So this is what happens with this sensitivity analysis of minimization diagrams. So we need to have a description of the capital T to compute the derivative. And then I'm not going to show any technical details of how it's done. I'm just going to explain the main ideas. So in the smooth case, you can easily imagine that you have many choices for the capital T. Now. So let's say if we have a family of parameterized shapes. And then for to define a capital T, there are many choices because we can, for a point X, we can just send it to the perturbed omega T in different ways. But for instance, we can have uniqueness if we choose only the capital T in the normal direction. We just quotient the tangential perturbation basically, and we get a unique transformation capital T. And this is a basic idea that we can generalize for non-smooth shapes. So typically for non-smooth shapes, what happens is that depending on the dimension of the object, you will have more or less freedom to move the point. So if you have an object of dimension 0, the motion is prescribed, because it's just your omega T is already given. So for small perturbation, you can compute, for instance, this. You will typically compute this theta at the vertex using the implicit function theorem, for instance. And then when you are on the interface, which is of dimension 1, then you have 1 degree of freedom. And so you can easily, for polygons, you do the linear interpolation between two vertices because you know that the interface is a straight line. And when you are inside the domain, then it doesn't really matter. You can take any direction because you are inside the domain. You only need to have some continuity of the transformation at the boundary of the polygon, okay? So it works in the same way for curvilinear polygons. So let's say I have the intersection of two disks, which is my cell VI. So this is like a curvilinear polygon. And you can see that the motion of the vertex is prescribed if your shape is parameterized. So you can determine this theta at the vertex just applying the implicit function theorem typically. But for the other points on the regular part, then you have the choice. So typically you have one direction which is prescribed and the other ones is free to choose. And so you just need to extend the value that you have obtained here on the whole interface to get capital T that is well defined. And so the construction of the capital T at regular point is less straightforward than in the case of polygons because you cannot do the linear interpolation directly, but the idea is similar. You need to define a kind of extension to define it. Okay, so to summarize these ideas, considering this principle and assuming that the geometry is not degenerate, I'm going to explain this briefly afterwards. To build the capital T, we can proceed as follows for the curvilinear polygon. So first, we determine the T at singular points using the implicit function theorem. Then we extend the capital T on the arcs, and then we extend inside the domain. And we always need to be careful that the capital T is a bi-Lipschitz function. We need the bi-Lipschitz property to compute the change of variables, to compute the derivatives. Okay, so now how can we apply this to compute the shape sensitivity for this kind of problems? So we have, let's say we have constructed this mapping T and it's bi-Lipschitz for all T. Then we have a set of parameters, which are the sites, for instance, for Voronoi. And we have a small perturbation of the sites. Let's say, for instance, that we want to compute theta in the normal direction to the shape. Then we get this type of formulas. And so here I have emphasized in red the perturbations because the theta in the end is just a parameterized function of this perturbation of the sites. So if for an optimization algorithm, what matters is this delta AK, because then you will get your derivative of your cost function will be a gradient, and this will be the perturbation. So you can see this kind of formula reminds a bit of level sets functions. It depends on the gradient of the functions that are involved. So it just generalizes the case of the level set methods. And this is a formula that is valid on the interface between two cells I and K. Sorry, my voice is bad. So you can do something similar at in the tangential direction. So this would be at certain vertices. So typically it's like at a triple point in the Voronoi cells, okay? So imagine the Voronoi cell, you have your interfaces. You can compute the perturbation in the normal, but you can also compute the tangential perturbation at the triple point. And of course, because the triple point is at the interface between three cells, is going to depend on the three perturbation of these sites, okay? And here you have these terms that depend on it's just geometric quantities. And you can see that they depend also on the gradient of the function that define your minimization diagrams. There's also this function Q, but it's also purely geometric function that depends on your function phi. In the paper, we also consider the case of a fixed boundary. So this means that if you have, for instance, a boundary of your whole domain, and you have an interface that cuts it, then this boundary does not depend on the Voronoi diagram. It's just something, it's like your box, okay? And you can still compute the value of theta in the tangential direction in this case. And this is sometimes really useful for application. Okay, so let me just show you a more concrete application. So let's say you have a cell integral, which is a volume integral with a perturbation of so you make a small perturbation of your control parameter A. So there's no PDE involved, it's the function f, just like in the previous talk. And then you can compute the gradient of G1. So it has the typical shape in shape optimization. You would get some integral on the boundary of f theta times n. So instead of the theta times n, you have this one. But this is because the theta times n is precisely this. And so it's really the same formula as in shape optimization. And you can see that you get the gradient of your G, which is just a finite dimensional function. And so it's like a composed function of a shape function and a finite dimensional function. So in the end, you can write this gradient explicitly by taking out this delta AK outside of the integral. And you have a sum over all the cells. So it's a sum, in fact, over all the cells interfaces. So the way you would compute this is that you're going to sum over all the cells and over all the interfaces in the cells. So I'm just showing the result in the particular case of the Voronoi because it's a very important application. So in this case, this is the general case for minimization diagram. So you have this gradient of phi k, which defines the minimization diagrams. And here in the Voronoi case, these functions, they are just this Euclidean distance to the site, so they simplify a lot. So you get this kind of a simple expression for this matrix M and this function Q. Okay, so now I want to briefly discuss something that I did not talk about until now, is that all these results, they are valid if you need some non-degeneracy condition on the function phi. It's the same as in the level set method. In the level set method, the gradient of your function phi cannot be zero on the interface, obviously, because otherwise it makes like a thick interface. So here it's exactly the same, it's just a bit more complicated, the condition. But it's basically a condition on the gradient of phi. But because phi is vector valued, then the condition is more complicated because you need to have conditions on the interfaces and at the triple points. Okay, but it's basically a condition that the gradient of the Jacobian matrix of this function has the right rank. Okay. So what are the difficult configuration is when, for instance, a typical problem is when more than 3 cells meet at a vertex in a Voronoi diagram. because this configuration, they corresponds to, it's not really a topological change, but we can see this as a topological change in the sense that the structure of the diagram is changing. So here I'm showing you an example. So a typical example is when you have a quadruple point here. So it's a point which is, it at the same distance to 4 different sites. You can see what happens if you take 2 of these points on the left, on the right. If you extend them a little bit, then a new interface is going to appear here. But obviously, if you do the same for the one which is up and down, then you will have the interface in the other direction. No? So it's the same problem that they have in the numerical approximation of PDEs with the so-called edge flipping. You change the structure and then your edges are, it's a similar problem. And so this kind of situation for the theory, it's you need to exclude this kind of situation to do the analysis, but still in the numerics, it can still work even if you have, if you need to exclude this kind of situation in the theory. So in fact, you can also analyze this situation. It's a bit like in shape optimization. You can consider the topological derivative, and then you can make some specific asymptotic analysis to study this kind of situation. So here you can also study the derivatives of this function at this kind of situation, and you can prove some partial result, like you can prove that this function is a Gato semi-differentiable in a certain direction. And the expression that you obtain is the same as in the regular case. You can even do this for edge function, which is more singular. You can also prove the Gato semi-differentiability in this case, and you obtain some expression for the derivative. So you can study these cases to some extent, but the analysis depends on the geometric configuration. So it's more difficult to have a really general theory for this kind of situation. We have until what time, sorry? Until 15? Okay. Okay, so this is an example of application. So there's no PDE involved, it's just the optimization of the cells. So you can see it's a Voronoi diagram. So here the idea is that we want all the cells to have the same value. So this function, you can see that it means that we want that each cell as the, like if k is equal to 1,000, then we want to each cell to have 1,000 of the value of the total area of this shape. And you can see that this is an optimal solution. So in fact, you can check that these areas, they all have more or less the same area. But of course, the shapes don't need to be more regular than this. So it means you can get some quite irregular distribution, but they have the same area, and you can observe this here. So for the optimization, you can mix different type of criterion if you want to optimize your cells to have certain shapes. And to do this, we apply the formula that I've shown before. So for instance, for this J1, we can compute the gradient. So the gradient of this function Ji, it's given by this formula, which is basically the formulas that I've shown before, but with a specific function f. So you can see it as a simple expression which depends on the midpoint here between 2 vertices of an interface E, and it depends on the perturbation of the site. So for each cell, you have to consider all the different segments on the cells, and you sum over the different segments. And then for each segment, you're going to have the perturbation of the cell and the one of the cell which is neighbor with respect to this interface. So that means you go over all the interfaces in the cell, and the delta AI is always the same, but this AK, it depends on what is the neighboring cell. And then you need to sum over all these terms. So this term is just for one cell, and you need to do the same for the other cells. Okay? So that's why this index K here, it depends on the interface. And then you can, in the paper, we have considered several type of functions. So there's 5 or 6 functions. So this is another example where we want to avoid small edges. So here, basically, the idea is that we want to prevent that an edge on a cell is too small. So this C2 is controlling the size of the cell. So if C2 is equal to 0.5, it means the smallest edge should be at least 50% of the average size. So here we just impose 10%, 20%, 30%, 40%, 50%. But when you increase the C2, the problems, of course, becomes more and more difficult. And it was difficult to go beyond 50% here. But you can see that you get a good improvement. Here, the color map represents the quality of the mesh with respect to this criteria. No? So the darker the cell, the more unbalanced are the sizes of its edges. But you can see that when the C2 is increasing, then you get a much better criterion here. Okay, and I'm going to finish with the PDE case. So what I've shown so far, there was no PDE involved. But the theory works exactly the same. It's completely independent of the fact that there's a PDE involved or not. It's just for the application, we started with something without PDE because it's already complicated. But now at the moment, we are working on a problem that involves a PDE. So a typical example would be like an inverse problems, like for instance, electrical impedance tomography. So let's say you have your domain that is divided into cells inside the old D, so it's the square here. So it's always the same figure. You can see here the sites. And then you have a piecewise constant conductivity sigma. So sigma is equal to a different constant in each of these cells. Okay? And U is the solution of a Neumann problem here, and with the G on the right-hand side, which is an applied boundary current. So in this type of problems, you have, as a data, you have your applied boundary current, and you have your H, which is the corresponding measured boundary voltage. So you have this Cauchy data, GH, and you can have several measures. That means you apply several G's and you get several measurements H. And using this data, you want to reconstruct the conductivity sigma. Okay, so typically you can minimize this type of cost function. So here the sigma is going to be a function of A because it's only determined by the position of the sites. If you assume that you know the values of the conductivities. But you can also define other cost functions. So here, this is just an example of cost function. And then we can compute the gradient of J with respect to the A, where A is the position of the sites, using the shape derivatives. So typically it works like this. So let's say you have a cost function that has a distributed shape derivative, which you can write in this form. So it's not that you can always write the distributed shape derivative in this way, but for in some cases you can write it like this. So typically, if you have a shape derivative of this form and that the S1 is smooth enough, W11, then you can transform this into a boundary integral, which is the usual Adama expression that we have for the shape derivative. And then you combine this with the expression that I've shown before, and you will get this expression for the gradient of J. And so you get a sum over all the cells. For each cell, you have a sum over the interfaces. And this is the usual term in the shape derivative. And this is like your theta times n, okay? So in the end, it's a function, it's a gradient. So it's a finite dimensional object. And each gradient is this sum of some integrals that you have to compute on the interfaces, okay? It also works if you have a shape functional that has terms which are boundary terms. It works in a similar way. And then, so here the sum is over the interior edges of the omega I, because the one which are on the boundary of D, they don't move, so the derivative is 0. And then here the K is the index such that the E is the interface between two cells. No? Okay, so I'm going to conclude here. So I've shown that the parameterized minimization diagram, they are a powerful tool for multi-phase shape optimization problem where non-smooth shapes appear naturally. And we can do the sensitivity analysis using non-smooth shape calculus, but we need some condition to avoid the degeneracy. But we can still make numerical calculation even though the theory does not cover all the cases. So now we are working on problems involving PDEs. And here it really leads to some interesting problem because the main issue with problem with PDEs are the corner and edge singularity that play an important role to prove the shape differentiability. So they can really sometimes have a very negative effect, like they can prevent you from writing the boundary expression of the shape derivative, or they can even destroy the shape differentiability if the singularity is too strong. So this is really something you have to do case by case. For each PDE, you will get different singularities. And for the numerics, it's also difficult because then you really need some very accurate computation near the interfaces, and you have these moving interfaces. So if you use a fixed match, it's not so easy. So here, this is really, I think, relevant with the previous talk, where we see this moving shapes for the level set method. So this would be all something similar that would work for this kind of problems. So here I'm thinking in the near future of considering more advanced methods like CutFem, XFem to really have an accurate representation of the boundary. Okay, so thank you for your attention.